All right. For the Python Lab 5, we're just going to um, show you the code. I'm just going to explain the code from the example of lecture 17. Just as a reminder, for the linear triangle, the three shape functions in terms of x, y are given here. And we need also the gradient of the shape functions with respect to x, y. So that's the B matrix. And that one for the linear triangle is given here. And then the problem that I solved um, was example 8.1 in lecture 17. All the details are in the slides. We solved the problem with two elements, 4 nodes total. And this is the same problem that I solved by hand in the lecture. I'm just going to show you the code. So that's lecture 17 C code. It's already uploaded. There's 2 elements and 4 nodes. The coordinates of the nodes are given here. So there's, first node has x and y 0, 0, 2, 0, 0, 1, 2, 1. And these are 0, 1, 2, 3. Just I have -1 for the node number just because of the Python node numbering. And then the element connectivity, so which nodes make each element is stored in this element array. So the first element is made out of nodes 0, 1, 2, and the second element is made out of nodes 1, 3, and 2. Then additionally, there's a flux at the top. There's also a flux at the right, which is 0. And then I created this new array that we haven't seen before, this element edge flux array. Now, this only works if the flux is constant over the edge. Otherwise, it won't work. But if the flux is constant over the edge, this will work. And this essentially what it's doing for the triangle would be what is the flux over each edge of the triangle. So for element 1, so triangles have 3 edges. For element 1, the first edge has 0 flux, the second edge has 0 flux, and the third edge has 0 flux. How do I know that? So the first element is this, because the node numbering for this element is, this is node 1 of the element, this is node 2 of the element, this is node 3 of the element. Then this will be edge 1, which has an essential boundary condition, therefore no flux boundary condition, so flux will be 0. I can treat it as 0. There's some reaction, but for the purpose of the force term, I can treat it as 0. Then this will be edge 2, and that one is an internal edge, so no flux. And then this is edge 3, and that one is also essential boundary condition, so no flux term. So that's for element 1. So that's why I have this 0, 0, 0. Now for element 2, note that my nodes are, this is node 1 of element 2, this is node 2 of element 2, and this is node 3 of element 2. Therefore, this is edge 1, and that one has a flux boundary condition, but the flux is 0. This is edge 2, and that one has a flux boundary condition, which is 20. And this is edge 3, and that one is an internal node, so I'm just going to put a flux of 0. There is some flux, but this, what I'm interested in capturing here is the external flux. So if there's an internal edge, I'm just going to add 0, and there's nothing, that doesn't change the solution at all. The only thing that is important is that whenever there's an applied flux that is non-zero, I put it here. So for the second element, as I said, the first edge has a flux but is 0. The second edge has 20 flux, and the third edge has 0 flux. And finally, these are the other parameters of the problem. I need to define the area function, which I've given you before, and then I need to solve the problem. The first thing that I need to do is assemble the stiffness matrix and the force vectors. So here you can see that the stiffness matrix, the global stiffness matrix, is the size of number of nodes times number of nodes, just as always. The force source term is a vector of the number of size, the number of nodes. The flux source force vector is the size of the number of nodes. Just as always, I have a for loop over the elements. So I have a for I in the element number, and then I can print it out. Each element is made out of 3 nodes. So here what I'm doing is I'm going to read the global node number corresponding to the local node number of this element. So element I local node 0 is global node N1. Element I, local node 1 is node N2. Element I, local node 2 is node N3. Then given that I have the global node numbers N1, N2, and N3, I can use this to access the node X array. Note again that for accessing the element array, I access through I, so that's the element number, and then the local node numbers 0, 1, 2. And I get global node numbers N1, N2, and N3. And then once I have these global node numbers, I can access the X and Y coordinates from the node X array. And this is what we have been doing before. So hopefully this is familiar. So for the first node, X1 and Y1, that will be node X, N10 and N11, and so on. Given the XY coordinates of the triangle, I can get the area, I can get the B matrix, and again, this is just directly copying the matrix that I gave on the slide. And then I can get the element stiffness matrix. So for the linear triangle, there's no need to do integrals because everything is constant. So the integral reduces to having the area here, and then B transpose times D times B. But for nonlinear elements or quadrilateral elements, you would have to do the integral of B transpose D times B. That's it, and then I need to do the assembly. And for the assembly, again, just as always, I need to go from local node number to global node number. So local number node 0 goes to global node N1. Local node 1 goes to N2. Local node 2 goes to N3. And so, for example, KE00, 0 goes to N1, 0 goes to N1. KE01, 0 goes to N1, and 1 goes to N2. 02, 0 goes to N1, 2 goes to N3. And so on. I have to do this for all the entries of the KE matrix. Since this is a triangular element, has 3 nodes, therefore KE is going to be a 3 by 3 matrix. So I just need to do this 9 times for all 9 combinations. And that's it. And this is basically the same as the assembly that I do by hand. It's just automated. Then I need to get the element force vector for the source term. And that one, again, in general, you would have to do this integral of the vector of shape functions times the source term. But because S is a constant, then I can take it out of the integral, and then the integral is trivial. It's just area over 3 times 1, 1, 1. Again, this is just because S is a constant. And I did the derivation in class for the source term. You know, you can take out S, and then these integrals are just area over 3. And then the assembly, same as before, 0 goes to N1, 1 goes to N2, 2 goes to N3. Finally, the force term due to the flux. So now here you need to do each edge separately. And this is why it was convenient that I defined this element edge flux. So before I show you the code, let me show you what I did in class very quickly. So in class, what I did was I need to integrate over the boundary that has boundary condition. Now, it doesn't harm to do the integral over every edge as long as I put a Q of 0. Then, you know, I will just be adding zeros and that will be fine. So for element 1, actually there's no edge that has a flux boundary condition, so I should get 0, 0, 0. For element 2, I do have 2 edges that have flux boundary condition. So remember that the local node numbering for element 2 was, this was my node 1, this was my node 2, and this was my node 3. So in this case, edge 1 has a flux boundary condition, but it's 0. So at the end of the day, the integral is going to be 0. Edge 2 has a flux which is 20, and edge 3 is an internal node. So that one will not add anything, but I could add zeros and it wouldn't change anything. So here, as I said, the right edge, because I'm integrating 0, then it's going to go away. The internal node will just add 0, so it's going to go away. The only one that is non-zero is this. And what I told you in the lecture video is that because the flux is a constant over the edge, I can take it outside of the integral, and then I just need to integrate the shape functions over the edge, and the integral is just the length over 2, but only 2 shape functions are non-zero over the edge, and 1 shape function is going to be 0 over the edge. And you can see here that for the top edge, that one is edge 2 of the element, and for edge 2 of the element, shape function 1 is 0 over that edge, whereas shape function 2 is non-zero over edge 2, and shape function 3 is also non-zero over edge 2. So I'm going to get 0, length over 2, length over 2. So how do I generalize this? For edge 1, I can calculate the length of the edge, and then I can create a force vector corresponding to edge 1, and I'm going to multiply the flux for that element over the first edge. So this would be, what is the flux on element I on edge 0? That multiplied by the length of the edge over 2 times the integral of the shape functions over the first edge. And here's where you need to notice that 2 of the shape functions are non-zero over edge 1, but 1 of the shape functions is 0 over edge 1. So let me show you again. So edge 1 is the edge on the right. That would be edge 1. And you can see from these pictures, here I have N1, N2, and N3, that N1 is non-zero over edge 1, so that one will contribute. N2 is also non-zero over edge 1, so it will also contribute. But N3 is 0 over edge 1. So here, for edge 1, I need to multiply, again, the flux over edge 1 times the length over 2 times only shape functions 1 and 2 contribute. Shape function 3 is 0 over the edge 1. Then for edge 2, I also need the flux of element I over edge 2 times the length of the edge over 2 times the shape functions that are non-zero over edge 2. So in this case, you can already see that the only non-zero shape functions over the edge 2 are 2 and 3. So the shape function 1 is 0 over edge 2. Finally, for the flux over edge 3, get the length of the edge, and then the force term would be the flux of element I, edge 3, times, it's 2 here because of the indexing, but it's the third edge of the triangle, times the length of the edge over 2, times the shape functions that are non-zero over edge 3. And those are, if you check it out, so edge 3 is this edge right here. So you can see here, N1 is non-zero over the edge 3. N2 is 0, so N2 is 1 here and goes to 0 over edge 3. So that one's the one that's going to be 0. And N3 is non-zero over edge 3. So that's why I have here the 1, 0, 1. And that's it. Then I need to assemble. So from 0 to N1, from 1 to N2, from 2 to N3. Again, note that I am adding actually a flux term for every edge for every element. So it seems like I'm adding a flux term for every element for every edge. But in reality, if I just put a bunch of zeros in my in this element edge flux array, then I'm actually adding zeros. So there's no harm done, as long as I do have the fluxes that are non-zero in the correct element and edge. So other than that, I'm just going to be adding FEQ1, FEQ2, and FEQ3 for the flux over edge 1, 2, and 3. But again, as long as I put zeros whenever I have to put zeros, it should be fine. This is what you get. Solution is the same as always. Need the number of essential boundary conditions. Need the value of the temperature on the essential boundary conditions. In this case, they are fixed to 0. Matrix partitioning as usual, and get the solution. So that's it.